Hi there, welcome back. This is lecture 5 of Machine Learning from Data, where we're going to begin our discussion of training versus testing. Basic question: does E out approximately equal E in when you're learning with an infinite hypothesis set? Okay, and this is a nice lecture because at the end I'm going to give you a combinatorial puzzle to work on. So stay tuned. But first, let's talk about where we were from last time. Okay, so last time we discussed the feasibility of learning, and we boiled it down to two basic steps. The first step is, can you ensure that E out for G, the final hypothesis from learning, is close to E in of G? And if so, then you've established the first step of learning. And then the second step is, go and check, is E in of G small enough? Okay, if you can get both of those to work, then you can conclude that E out is low, and then you've learned G is approximately equal to F. Now, to help us with the first step, we have this Hoeffding bound, and we generalize the Hoeffding bound to the case of finite hypothesis set, and it says that when you choose G, the E out of G is linked to E in of G by the generalization error bar. And this generalization error bar basically depends on the square root of the logarithm of the number of hypotheses divided by the size of the data set. And then there's this trade-off which says that as you choose a larger and larger hypothesis set, then you'll get lower and lower in-sample error, but you'll pay a price, and this price is the price that you pay for having the flexibility to choose the hypothesis set from a larger and larger set. And this price, you can think of it as a model complexity price. Okay, and when you add these two, that's when you get this bound for E out, and this purple curve is sort of heuristically showing this bound, and you can see that it has a U shape, which means that there's some optimal hypothesis set size, and this is the size that you should pick. It depends on the number of data points, and of course it depends on the nature of the problem, which is how does E in drop as you increase the size of the hypothesis. You can think of E in as you're training to take a final exam, and you have a practice exam, and E in is how you perform on the practice exam. And why is that not why is it a tricky situation there? Because you might memorize the practice exam, you might focus on training only what you need for the practice exam. That's kind of like the learning algorithm might pick a final hypothesis G that's only focusing on the data set. Okay, but what really matters is when we come to test you with the final exam. Okay, so that's this issue of training versus testing. Okay, now we're going to embark on the theory of generalization. And what is the theory of generalization going to accomplish? Well, let's put on the top here, what we accomplished with finite hypothesis sets. And the theory of generalization is going to essentially tell us the same thing, almost. There are going to be some subtleties, but it's almost going to tell us the same thing for infinite hypothesis sets. So, in other words, we're still going to try to get a bound of the form E out of G. Now, where G is coming from learning out of an infinite hypothesis set. So E out is linked to E in by an error bar. And the error bar looks very similar to the error bar for finite hypothesis sets, which is the top row. Some slight changes in constants, so the 1/2 becomes 8 in bold here, the 2 becomes 4, and then the main change is that we're going to have to give up this notion of the size of the hypothesis set as a way to measure the model complexity and replace it with something that's a little bit more efficient, that sort of estimates the true complexity of the hypothesis set more carefully. Size is a kind of a rough estimate of how complex is a hypothesis set. Okay, so this new bound is going to be applicable to infinite H. And that means that we can implement our two-step process with infinite H with a theoretical guarantee for the first step that E out is close to E in. Okay, now what's going to allow us to do this? Because when you go back to how we proved the generalization of the Hoeffding bound for finitely many hypotheses, there was one fundamental thing that came into play, which was this union bound that said that G comes from the hypothesis set H, and if a bad thing happens for G, then it means that a bad thing must happen for one of the H's, and to bound that probability, we take the union bound, the OR. So we say that a bad thing for H1 plus a bad thing for H2 plus a bad thing for H3 and so on. So the union bound was instrumental in getting us the Hoeffding bound that's on the top here. Okay, but we can't apply the union bound with infinitely many things. So we have to fundamentally change the theory in such a way that we might be able to apply some related probabilistic bounds. Okay. And so here's the basic idea. The basic idea is that the size of the hypothesis set is overkill. Now to sort of to show that to you in a very trivial way, consider a hypothesis set which consists of all hypotheses that are the same. So you have H1, 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 M times. Okay. Now, in this case, G is basically restricted to H1. So it's effectively a hypothesis set of size 1. Okay, but when you just look at the size, it's huge, it's M. Okay. And, the bad event that occurs for G is when its E out is far from its E in. And, that was the sum of the bad events for each of the hypotheses. But, if the bad event occurs for one of the hypotheses, it occurs for all the hypotheses in this hypothesis set because they're all the same. Okay. So there's a huge overlap. There's a huge intersection in when the bad events occur in the hypothesis set. Now, my argument, remains roughly the same if instead of identical hypotheses, we replace the hypothesis H1 with something very close to H1, and then something very close to that, and something very close to that. So the hypotheses are technically different, but practically they may basically be the same hypothesis. They might only differ out at infinity, for example. Okay. So what that means is that when a bad event occurs for one hypothesis, it will simultaneously be a bad event for all the hypotheses. Okay, and so the probability that a bad event occurs for, one or the other is essentially the same as the probability that it occurs for one. And so we don't really need to multiply by the size of the hypothesis set. And that's captured by this picture here, which shows the bad events. So the green circle is the bad event for hypothesis 1. The blue circle is the bad event for hypothesis 2. The red circle is the bad event for hypothesis 3, and so on and so forth. And now we want to take, the union bound says I'm going to bound the size of the union by the sum of the sizes. Well, in this case, it's clear that the size of the union is much less than the sum of the sizes. Okay. So the bottom line is that the size of the hypothesis set is definitely a measure of its complexity, but it can be a gross overestimate when the hypotheses are very similar. Okay. And so we want a measure of the size of a hypothesis set, or effectively its complexity, that can capture the similarity between the hypotheses in it. In particular, if every hypothesis is basically the same, then the effective size is close to 1, not close to infinity. Okay.